and welcome to another WJEC A level physics question. This time is question 6 from June 2014's PH4 paper on electric fields which are currently in Unit 4. We've got three charges arranged as shown in the diagram and we've got some point P. And the first thing that we're asked to do in this question is to draw arrows at P to represent the electric fields due to each of the three charges. The key to this is to remember that electric fields are defined in terms of positive charges here. So we imagine that there is a positive charge at P. This 13 microcoulomb charge at the top left is positive and it would repel the charge at P. So we draw an arrow pointing away from P. Similarly with the 13 microcoulomb charge at the bottom, that would also repel P. So again we can draw an arrow pointing away from P. The negative 24 microcoulomb charge will attract the positive charge at P, so we draw an arrow to represent it to the left. Next we've got to calculate the electric field strength at P due to the minus 24 microcoulomb charge only, and we can use the approximation that 1 over 4 pi epsilon naught is 9 times 10 to the 9. So formula for electric field strength, let me turn the pen on properly. Formula for electric field strength is 1 over 4 pi epsilon naught Q over R squared. So we've got 9 times 10 to the 9 multiplied by the charge, which is minus 24 microcoulombs, but we're going to ignore the minus sign simply because we've covered its negativity by the direction of the arrow, over R squared, and if we return to the diagram we can see that it is 12 meters away from P. So if we put those numbers into a calculator we get a nice round answer of 1500 and a unit of newtons per coulomb or volts per meter. Never forget the units on these questions. Next we've got to calculate the resultant electric field strength at P, and again we can stick with that same approximation. So what I'm going to do is do this in steps to show exactly how we would do this. We're going to calculate the field strength due to one of the 13 microcoulomb charges. So I'll just call that E13 if you like. That's going to be 9 times 10 to the 9 times 13 microcoulombs, and again, if we look at the diagram, you see that these are 13 meters away from P. So we got over 13 squared. Putting those into a calculator gives us an answer of about 692 newtons per coulomb. Now we're going to add all of those fields together, but we've got to remember that field is a vector quantity. So what we're going to do here is we're going to find the components of these two fields in the horizontal direction. So that would be the 692 newtons per coulomb that we just worked out times cos of this angle, and this angle is theta as over here. Little trick here is that cos is adjacent over hypotenuse, so we've got a 12 over 13. So overall what we're going to do now is we're going to work out the total of these two fields by doing two lots of 692 times that 12 over 13. So that will give me the resultant field to the right. So it's going to be two lots of 692 times 12 over 13. And that gives 1278. And finally, the resultant field, E res or sigma E or whatever else you want to call it, is going to be the 1500 that we worked out for the field due to the 24 microcoulomb charge, and we're going to take away from it the value that we've just calculated. So 1500 minus 1278 gives us 222 to the nearest whole number. And because it says to calculate the resultant electric field, I'm going to put in the direction. That resultant field will be to the left. If it just said calculate the magnitude of the field, then I'd be happy to leave it as 222 newtons per coulomb. But remember, fields are vector quantities and do have a direction. Next we've got to show that the electric potential at P is 0. Well, our formula for electric potential is 1 over 4 pi epsilon naught Q over R, not R squared. So the total potential here, so let's call it V res if you like, would be 1 over 4 pi epsilon naught. Again, we could use 9 times 10 to the 9 if we like. Well, we've got two charges of 13 microcoulombs at 13 meters. And we've got one charge of 24, I believe it was. Yeah, 24 microcoulombs at 12 meters. Now one thing should make sure that we have a minus sign here, because that 24 microcoulomb charge was negative, and when we're working with potentials, signs are important. Now you might notice here that the 13 and the 13 will cancel to give 2 times 10 to the minus 6, and the 24 and the 12 will also give a 2 times 10 to the minus 6. So we have basically 1 over 4 pi epsilon naught times 0. In other words, the bracket is equal to 0. So it's important that we remember the minus sign for the 24 microcoulomb charge. Finally, a negative charge is released from rest at point P and encounters no resistive forces. We've got to explain in terms of energy and forces why the charge initially accelerates to the right, but eventually becomes stationary a long way away from these three charges. Well, first of all, the resultant field was to the left, and the resultant field shows the direction of the force on a positive charge. So the force on a negative charge is to the right. Just put in here a little explanation. It's opposite to the field direction. So the charge will accelerate to the right. Now the total energy of this particle at the start will be 0. It's released from rest, so it has no kinetic energy, and the electric potential at P is 0, and therefore there's no potential energy at 0. And from the law of conservation of energy, the total energy anywhere will be 0, and specifically at infinity, which is a long way away from these three charges. Also at infinity, the potential energy is 0 by definition. The definition of the electric potential at a point is the work done in moving a unit positive charge from infinity to that point, and if we're already at infinity, obviously there's no work done there. So if we have 0 potential energy at infinity, therefore the kinetic energy at infinity will also be 0. So the object, the charge here, must come to rest. And what that does imply then is if originally the force was to the right, sometime the direction of the force will change. So sometime along the journey, the direction of that force will change. Will reverse would be a better word, to make it clear that it would be a force to the left. Basically, we're looking for sort of any 3 out of the main points that we've got here. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.